Imagine driving through a city during rush hour. Two cities can have the same number of roads, the same number of cars, and even the same total space for traffic. Yet, in one city, traffic flows smoothly, while in the other, it comes to a complete stop. The same issue can be seen inside some clean energy devices. These are systems that produce little to no environmental pollutants during their operation. My work, my research focuses on one of these technologies, carbon dioxide electrolysis. The process uses renewable electricity to convert CO2 emissions into useful products such as fuels or industrial chemicals. What this means is instead of just reducing emissions, we are reusing them as a resource. However, there is a challenge. Inside of these devices is a material called a gas diffusion layer. It's a porous structure that transports your carbon dioxide to the reaction site. You can think of this material as a road network for your gas molecules where the pores are your streets and the gas molecules are your cars. And just like cities that experience traffic, these materials can experience something called flooding. In a separate compartment, we also have a liquid electrolyte that's required for this reaction. However, at large scales, this liquid can invade your microstructure, causing a blockage, preventing your gas molecules from flowing through. And this severely degrades the performance of your device. And one common solution is to just design these devices with as much space as possible to allow gas transport. However, surprisingly, two materials can have the same amount of empty space, yet behave completely differently. For example, in the top image, you'll see a device with poor connectivity. When flooding occurs, many pathways become fragmented and your CO2 becomes stuck. However, the bottom image shows an example of a device with good connectivity, where even when flooding occurs, there are still many open pathways for your gas molecules to flow through. And the surprising part is that these materials have the same amount of empty space in them. My research uses computational modeling to understand how changes in these microstructures can impact flooding and gas transport. By optimizing these devices, we can improve carbon conversion technologies and promote a cleaner energy future. Thank you very much.